All right, let's dive right into this. Welcome to This Explainer. Today, we are going to completely demystify exactly how we build roads from the dirt up. I mean, we drive over them every single day, right? But we're usually completely oblivious to the massive jigsaw puzzle sitting right beneath our tires. So today, we're going to act as project managers on a virtual construction site to build a very specific, highly influential type of road foundation. Get ready, because we are breaking ground right now. We are talking about the Water-Bound Macadam Road, or WBM for short. It's actually named after its early 19th century Scottish inventor, John Loudon Macadam, and it's what we call a flexible type of pavement. Now, what makes this so fascinating is that on our construction site, we aren't going to rely on modern chemical binders like cement or asphalt to hold the road together. No way. Instead, we are relying on pure physics, mechanical interlocking. By tightly packing crushed stones and filling the gaps with screening materials and water, we literally lock everything together like a massive, heavy-duty puzzle. So here is our blueprint for the build. We'll do a quick intro to WBM Roads, gather our 4 essential materials, prep the foundation, tackle the compaction and grouting, finish up with binding and curing, and finally, look at the pros, cons, and comparisons. We know exactly how we're going to build this, layer by layer. All right, Part 1, Introduction to WBM Roads and Setting the Stage for our build. 7.5 to 10. That is the exact thickness, in centimeters, of each individual water-bound macadam layer we are going to lay down. We don't just dump a massive pile of rocks out there and hope for the best. We meticulously build upwards, one highly structured 7.5 to 10 centimeter layer at a time. This ensures maximum density and strength throughout the entire pavement structure.
Moving right along to Part 2, the 4 essential materials, basically our engineering recipe.
Now, what's really interesting about this recipe is how specific it is. First, we need the backbone, coarse aggregates. This can be crushed stone, overburnt bricks, or even crushed slag. Second, the screenings. These are smaller stones, usually under 12 millimeters, used specifically to fill the voids between the big rocks. Third, the binding materials, like limestone dust or conker nodules. And notice that strict requirement? The binding material absolutely must have a plasticity index between 4 and 9 to perform properly. Though actually, if we use soft, crushable gravel for our screenings, we might not even need this separate binder. Finally, the simplest but most vital ingredient of the whole shebang, water, which brings it all together.
Okay, we have our recipe. Let's hit the site for Part 3, Preparing the Foundation.
Before we drop a single stone, we have to look at our geometry. 1 in 36 is the required camber, or cross slope of the road formation for areas that experience heavy rainfall. If the rain is just normal, we can use the gentler 1 in 48 slope. But why is this slope so critical? Because water is the absolute worst enemy of a WBM foundation. The subgrade must be shaped with this precise camber so water immediately drains off the sides and doesn't just sit there destroying the structural integrity of our foundation.
Let's walk through the first 4 physical, dry steps of our build. First, we excavate and deeply compact the dirt subgrade. Second, and this is absolutely crucial, we build lateral confinement. We construct earthen shoulders or curbs along the edges. Think of lateral confinement exactly like the bumpers in a bowling alley. If they aren't there, the rocks will just scatter everywhere when we try to crush them down. Third, we spread our coarse aggregates evenly to a thickness of about 75 to 100 millimeters. Finally, we begin dry rolling. We take our heavy roller, start at the confined edges, and gradually shift towards the center. We just keep rolling until the aggregates are completely mechanically interlocked.
With our dry stones locked in, it's time for Part 4, Compaction and Grouting. This is the heavy lifting.
So the crucial point here is this weight, 8 to 10 tons. That is the massive capacity of the smooth-wheeled rollers we are deploying on our site right now. These rollers are doing this serious heavy lifting, literally crushing and interlocking those aggregates into an incredibly dense solid mass. It's an elegant 19th century engineering principle, but executed with the absolute brute force of an 8-ton steel drum.
Now we really get our hands dirty. Step 1 here is applying the screenings in 3 or more gradual passes just to fill those large gaps. Step 2, we bring in the water tankers. We sprinkle water and begin wet rolling at the exact same time. Just imagine the sensory details for a second. The deafening sound of crushing stone, the thick, wet slurry forming as water forces the fine materials deep into the voids. We vigorously broom the surface to sweep those screenings in. Step 3 is grouting, ensuring every single empty pocket is completely filled.
Finally, step 4, we apply our binding materials in 2 to 3 very thin layers, sprinkling water and rolling continuously to lock it all down.
We are finally moving into part 5, binding and curing. The heavy lifting is done, and now, patience is our best tool.
And this brilliantly illustrates how we know we're done rolling. Site engineers don't just guess, they look for the slurry wave. When a thick, dense wave of wet slurry visibly forms and pushes just ahead of that heavy-moving wheel, it is the ultimate visual indicator. It tells us that every single void beneath the surface is packed completely tight and the layer is perfectly compacted.
But you can't just drive on it immediately. The timeline is super strict. First, the layer must sit overnight to set and dry. The very next day, we inspect it. If any voids have somehow opened up, we fix them and spread a 6mm layer of sand or earth over the top. Then, we enter a strict curing period of up to 10 days where the surface is kept slightly moist. If a project manager gets impatient, skips this curing step, and opens the road to heavy trucks too soon, it completely ruins the structural integrity of that meticulous 7.5 to 10 centimeter layer we just broke our backs building.
All right, part 6. Our road is cured and finished. Let's switch from builders to inspectors and look at pros, cons, and comparisons.
Let's weigh this out. On the plus side, WBM is a brilliant, highly economical solution. It uses cheap, locally sourced materials. It doesn't require highly specialized, trained labor, and honestly, it can handle a respectable 900 tons of traffic per day. However, because it relies purely on mechanical interlocking and not waterproof chemicals, it is highly permeable. It acts almost like a giant sponge. This makes it incredibly vulnerable to rain over time, which unfortunately leads to high maintenance costs, potholes, and a generally much shorter lifespan.
Let's move to and see how this builds into the modern era. How does our historic WBM road compare to its evolution? Wet mixed macadam, or WMM. Notice the huge shift in technology here. While we manually mixed our WBM right on site with stone dust and water, WMM is pre-mixed in a machine called the pug mill using cement slurry or bitumen. This one single change drastically increases the road's durability. We're talking a jump from just 3 to 5 years for WBM all the way up to well over a decade for WMM. It shifts the road's capability from light rural traffic straight to heavy modern highway use.
So basically, it comes down to this final verdict. WMM is an incredible foundational technique. I mean, it literally built the modern world and remains the absolute best, most economical choice for rural, low-traffic areas. But as vehicles have gotten heavier and faster, modern highways fundamentally require the modern materials and machine mixing of WMM to survive.
We'll leave you with this to ponder. We just built a road using principles invented in the early 19th century. As we look forward to smart highways and futuristic cities, how will these foundational ideas, like relying on simple mechanical interlocking and local materials, continue to shape the ground we walk, drive, and live on? Thank you for joining this explainer. Keep learning, stay focused, and next time you're out on the road, take a second to appreciate the incredible engineering layered right beneath your feet.